Let's continue with strategies of integration. So in the next exercise, we have a multiplication between a power of x and a function log of x. So by the definition that we had before in the strategies of integration, I should do this by taking parts. So I'm going to start with u being the log of x and dv being x. And you might be wondering why I didn't do the opposite. Well, because if I do the opposite, then I need to integrate directly log of x, and that might be something that you can do, certainly, but it might be more complicated to do. So let's see what happens if I do this in this way. So if I do u is equals log of x, then the u is 1 over x dx, and b here is going to be x squared. So this might not work. Let's see what happens. So u times b is going to be x squared log of x minus, and then the integral of b du. But b du here is going to be x squared 1 over x dx. So it's actually not going to be that bad, because it's going to be x squared log of x minus the integral of x dx. So this ends up being x squared log of x minus x squared over 2 plus c. You might be wondering, can I do it the other way around? And sure, you can probably do it by taking the other substitution, but it's gonna need that you're able to do the integral of log of x. So you need to have a very clear idea of if I pick the v is log of x, then you gotta know that b is the integral of log of x, that you actually also do by parts, and this is x log of x minus x. So if you know this, or you're capable of doing this integral first, then sure, then you can go, oh, okay, so u is going to be x and the u is 1 dx, and then when you do the integral of x log of x, this is going to be u times b, so it's going to be x squared log of x minus x squared as well, and then minus the integral of b du. Okay, and so this is going to be b, and so what happens here is, notice that you're going to have this integral here again, and this is much more complicated. Can I finish this up? Yeah, sure. So for example, I can move this minus x log of x to the other side, and I'm going to have that 2x log of x dx is equals to x squared log of x minus x squared, and then here I'm going to have plus the integral of x dx, and so this is going to be x squared square over 2. So this means that this is x log of x dx is going to be x squared divided by 2 log of x minus x squared divided by 2 plus x squared divided by 2 as well. Okay, and plus c. So it's a much more complicated route to get to that point. It requires that you have a lot of information, and you might make easily any mistake here. Probably this part here is going to cancel out, so I'm not really sure this is getting to the same point. So I definitely will recommend just going by this direction. Now, let's move on to the next integral. So for number 4, we have the integral of 2x cubed plus x minus 1 divided x squared. Now this is one of those that you can simplify arithmetically. You can simplify by doing algebra first, not arithmetically. You can do 2x cubed divided x squared plus x divided x squared minus 1 divided x squared. And so essentially we're just transforming this into a different set of powers. This is 2x plus 1 over x minus x to the minus 2, if you will. And then this is just going to be x squared. This is just going to be log of x. And this is just going to be, when I integrate this, is x to the minus 1 over minus 1. So this is plus x to the minus 1 plus c. And so the key here is in knowing that I can simplify each of the terms if I can do this division of each of the parts of the integral. So it's a simplification. Number 5, again, is a power of x by a trigonometric function. So this is a parts. And so I'm going to do u equals x squared. The u is equals to x. The v is going to be cosine of x. And b is going to be the integral of cosine of x, which is sine of x. So this integral is u times b, so x squared sine of x minus the integral of b du, so 2x sine of x dx. Now you might be wondering, but I still got a power here going on. Yes, but I'm still advancing because I'm reducing the power. So now this is power 1. And I can see this as x squared sine of x minus twice, and then I'm going to be doing parts here with this one. And so I'm gonna change my substitution here. I'm gonna go u equals x, and so the u is the x, and then again the v is now gonna be sine, and so b is gonna be minus cosine. And so this means that this is going to be minus u times b, so minus x cosine of x, minus the integral of b du, so minus and minus plus, and then b du will be cosine of x dx. And so overall, the final integral result is going to be x squared sine of x, and then plus 2x cosine of x. And then the integral of this is going to be sine, so plus sine of x plus c. So essentially the key here is knowing to recognize that I gotta use parts, and after that just doing parts. Sometimes I have to do repeated parts in the same exercise, like here. And that's how I proceed. Number 6, you see that is e to the square root of x over square root of x. When you have a composition of functions like this is kind of calling it for a substitution. And so here you can clearly see that probably if we eliminate that square root of x and we transform that into a u, it will be a much more easier function to manage. So if u is equals square root of x, then the u dx is going to be 1 over 2 square root of x, which is essentially the same thing that 1/2 x to the minus 1/2, in case you're taking derivatives of this as x to the 1/2. Okay, but why is it important to me to see this as 1 over 2 square root of x? Because this means that the du can be seen as 1/2 1 over square root of x dx. You see? And so now this integral here is just e to the square root of x times 1 over square root of x dx. And then I'm missing the 1/2, but I can add 1/2 here. And then because I'm multiplying by it, I'm just going to put out the 2. And so that's going to make it like I'm just multiplying by 1. And so now this integral transforms into 2 e to the u du. And that's it. This is 2 e to the u plus c after doing the integration. And then I come back to the original variable, 2 power to the square root of x plus c. Sorry, not 2, e. To e to the square root of x plus c. Okay. All right. So now number 7. Notice that number 7 has a bunch of things going on that makes me think a little bit more. I have this x squared plus 4, which is going to make me think that this is a trigonometric identity, or a trigonometric substitution that I can use. This x cubed is kind of weird, but it might be something that is going to produce just a trigonometric power integral, so I'm just going to go with trigonometric substitution for this. So I'm going to go x is equals to tangent of theta. Since remember, this shape x squared plus 4 calls for this type of substitution, and so then the dx is going to be 2 secant square of theta. Now if I plug this in the integral, this is going to be 8. 2 to the 3 is 8 tangent cube of theta, and this is going to be square root of 2 tangent of theta squared plus 4, and then multiply by secant square of theta to theta. Now then this is 8 tangent cube, and now this is going to be 4 tangent square plus 4, which I can see just now as 4 secant square, right, by identities, and by secant, the square of theta. And so this is looking more and more like a trigonometric power. So now this is going to be square root of 4 is 2, by 8 is 16, so I'm going to pull out that 16 out of the integral, and this is going to be tangent cube, and this is going to be secant cube. And so normally what will happen is that I gotta look for some kind of identity. It's not gonna be identity tangent, substitution tangent, because the substitution tangent gotta give me secant square, and I only have secant cube. But notice that I can kind of remove one of those tangents and secants, and so if I do that, now I'm gonna be with tangent square, secant square, and I'm gonna be with secant of theta, tangent of theta, which is the derivative of secant. So this is telling me, the substitution should be secant. And so what happens with that is that now I can transform tangent square into secant square minus 1 times secant square times secant of theta, tangent of theta. And so with this, I can go with the substitution u equals secant of theta. And so the u is, of course, what we were expecting, secant of theta, tangent of theta, theta. And this is the du. And this transformed into 16. This is u square minus 1. U square here. And then du. And so, of course, then this becomes 16 u to the 4 minus u squared du. And then this is going to be 16 u to the 5 over 5 minus 16 u to the 3 over 3 plus c. And then at this point, I can replace my first substitution, secant of theta. And so this is going to be 16 over 5 secant to the 5 of theta minus 16 over 3 secant to the 3 of theta plus c. It seems like we're done, but we're not done, because we have that the substitution initially was x over 2 tangent of theta. So we're going to have to go to the triangle. And so if this is tangent of theta, it means that x is this, x is the opposite, and then 2 is the adjacent, and then the hypotenuse is going to be square root of a square plus 4. And so I need the secant. The secant is related to the cosine. And so cosine of theta is just going to be essentially adjacent over hypotenuse. And secant of theta is going to be the opposite. It's going to be this backwards. 1 over cosine, right? So x squared plus 4 divided by 2. And so this now is going to transform into 16 over 5 x squared plus 4. And so because this is a square root but power to the 5, this is going to be to the 5 over 2 minus 16 over 3. And this is going to be x squared plus 4. Because it's power to the 3, is going to be to the 3 half. And I can't forget that I'm having this 2 over here. So this is going to be by 2 to the 5, which is 32. And here's 2 to the 3, which is going to be 8. Okay.